Thank you very much. It's a great pleasure to be here. Thank you for organizing this nice meeting. I'm going to talk about debugging machine learning. It's a joint work with Gabe, Cadamuro, and Jerry Zhu. And let me first explain what do I mean by debugging machine learning. And I do that by drawing the analog between machine learning and just standard programming. So actually they're very similar. In standard programming, we kind of write the program, compile it, and get the executable. In machine learning, we create a data set, train a model, and execute it. So in a sense, machine learning is the same thing like as standard programming, but instead of writing the program in C or Java, we write it with data. And instead of calling the person who creates the program a programmer, we call them data scientists. So it's very similar, but actually this picture is too simplistic because programming does not look this way. Programming is an iterative program. You know, we can build a quick poll here. How many people here, whenever they write a program, they just hit it at the first time? And okay, just one. And how many of you do need to go into cycles of debugging and testing? Yeah, a few more, right? So actually it's an iterative process, right? So we write the program, compile it, we test it, find some problems, use some debugging mechanisms to find the root cause of the problem, and go back to the code and fix it. But actually, machine learning is an iterative process as well, right? So we create a data set, train a model, test it, find a problem, try to find the root cause of the problem, and go back to the data and fix it. But the difference is that in programming, we already have well-established methods of how do you do this debugging process. We have tools, we have methods ranging from the simplistic way of adding printfs at different places in the program, all the way to trace and step and breakpoints. But in machine learning, we don't have these well-established tools. We have attempts, mostly by people here in this room, trying to develop these tools, but most of them try to focus either on specific algorithms or specific types of data. But we don't have anything we don't have much that goes in terms of a generic method to do that. Well, what do we mean by machine learning bugs? So what are we looking at? And it's important to emphasize that much like when we debug a program, standard program, where we assume that the compiler is correct and it's most likely that the problem is in our code, the same thing here. Let's assume that the training algorithm is correct, but if there is a problem, it's probably in our data. And what kind of problem can we expect to see? We might be having some features missing, we might have a skewed sample, we might have some instances which are mislabeled. All of these can lead to bugs in the model that we are going to train. And we're looking for a debugger that can work across different data types, meaning images, if I train an image classifier, or maybe if I work in the medical domain, it's going to be the medical record of a person. We want to use the same philosophy across different data types and across different learning algorithms. Again, if I'm using decision trees, neural nets, linear models, I want to be able to use the same philosophy. Now, keep in mind that it might be that the implementation of under the hood of the debugger might be different. Much like a debugger for C and a debugger for Java might be different in terms of the implementation. But me as a user, I can use the same philosophy whenever I use them. If I put a breakpoint, it will stop there, regardless if my program is written in C or Java. So what we propose as a method is a hint. And what is a hint? A hint is a debugger that gives you, whenever you have a bug, it gives you a small subset of the training data that has large influence on the bogus prediction. So let me go a little bit in more details on this definition. So first of all, we want to have a hint which is small. And small allows the human to understand it. So if I tell you, if you have a wrong prediction, I'll tell you, look, it's somewhere in your training data, and your training data has millions of examples. That's not helpful. But if I can limit it down and say, look, here's 5, 10, 20 examples, which probably include the problem that you're looking for, that's something that we can handle. It also has an influence on the learning algorithm in that if we fix that, the fix is likely to be local and not going to turn all our model around. It we're just going to fix the problem that we're interested in. The hint is a subset of your training data. And the advantage of that is that it's going to speak the language that the data scientist expects to speak. Meaning, if I work on medical classification, probably I'm used to seeing medical records. So the training data is made of medical records, and the hint will be medical records. If I'm working on image classification, then I'm used to looking at images, and the hint will be images. And finally, the subset has to have a large influence on the box prediction, meaning that if I change something on this part of the data set, it's likely to change something on the example that I care about that had the bug. So it's not just a random subset of the training data. It's actually something that is selected with respect to the training algorithm and to the example that I care about. So we spent most of our study trying to come up with ways to find these hints. But instead of spending the time here explaining how do we do that for different algorithms, I want to spend the rest of my time showing you some examples of how does it look like. And the first example that I want to give is actually a real-world example that happened to us while working on this study. And a group from Bing, from the search engine, came to us, and they had a problem with a component of the search engines that is in charge of doing paraphrases of the query that we issue in the search engine. So whenever you issue a query, like the query here, Portland, Oregon, but Oregon is misspelled, there is a paraphrasing engine that looks at your query and tries to paraphrase it in a way that is more likely to yield the result that you care about. For example, in this case, it saw that there are no results for this query, but actually if you change it and correct the spelling in this case, actually you can find results which are relevant. So they were working on improving this mechanism, and they just built a new model which was actually better than the current one that they had in terms of accuracy on average, but it was making some embarrassing mistakes. So embarrassing that actually they couldn't use it. So here's an example. When they issue the query Portland OR, the current model kind of interpret OR as the abbreviation for Oregon, and obviously showed the result for Portland, Oregon. However, the new one decided that to drop the OR and just issue the query Portland, and therefore showed result on Portland, Maine. Now, this is embarrassing, right? The user asks you explicitly, I'm interested in Portland, Oregon, and you show a result on Portland, Maine, you just don't get it, right? So this is a showstopper. Now, the question is, what do you do about it? So they just trained a new model. It's on average better than the current one, but you have this bug. How do you go about solving it? So you might say, let's go over the data, but the training data in this case consists of millions of examples. It's not something that you guys can just scan and say, oh, here it is. You can try to look at the model, but the model here consists of hundreds of decision trees. So again, it's too big to just scan it and try to see what's went wrong. So instead, we use this method of hints, and this is what we found. So this is a short list of examples, the hint that the debugger gave. And each example from the training data consists of the original query and a paraphrasing of this query, and the label says whether this paraphrasing is a good paraphrasing or not. So for example, the first example that you see here said that taking the query Dayton TN and converting it to Dayton is a perfect substitution, right? And if you look at the last one in this list, taking the query F statistics and converting it to statistics, again labeled as a perfect substitution. So first of all, you see that it kind of makes sense what the decision that the model made kind of makes sense. It's aligned with the data that it was seeing, but you see that this data is kind of bad, right? Taking Dayton, Tennessee and converting it to Dayton is a bad substitution. Taking F statistics and converting it to statistic is a poor substitution. And basically, just looking at this short list of examples, you immediately see that there are some mislabeled examples in the training data. And once we backtrack them, we found that there was a stream of data coming to our training data, which was corrupted. and fixing it, just fix the problem, and we ended up with a good model that we can use. So just a word about the way we select the hint. So you might say, if I have an example, let's look at the feature value and try to find other examples which have similar features, for example. But the model does not work this way. For example, if you look at the decision tree, from the point of view of a decision tree, two examples that end in the same bucket are identical. And they might differ on many, many features, but the model doesn't look at these features. So there is no point on comparing them on these features. So you want to use, when you select the hint, you want to take into account how your model works. And here's another example to demonstrate that. Here we looked at images and we trained neural networks on these images. This is a Cypher data set. And now we took one of these images, this little airplane over here, and we tried to see what would be the hint if I would tell you that the classification for this image is wrong. So if we just look at the pixel-wise comparison between images, this would be the result. So depending if you use L1 or L2 distance, these will be the hints that you will get. And as you can see, these are images that share a little bit in terms of their colors being used, but they don't make much sense. However, if we use the proper method for neural nets, this would be the hint. I don't know if you can see it at the bottom, but these are basically all of them images of airplanes. And now it makes sense that this is actually what the model looks at as a similar example. Let me give just another example just to see yet another different type of data. Here is data about flight delays. All of us care about, we were flying in, probably most of us. So we have this data, and you have information about flights, when and where is it, what airport did it depart and get to, and whether it was delayed by more than 15 minutes or not. And you want to make a prediction for your next flight, is it going to be delayed or not? So we trained a model using gradient boosted trees, and for this specific example, it was making the wrong prediction, and we were trying to see why. So we generated the hint, and this is the hint that it was generated. Again, since we were training something on flights, the hint is just a list of flights. And you can see that most of these flights, you can see the label over here in your right, that most of these flights were not delayed. So it makes sense that our model predicts that our flight would not be delayed. But now we can start investigating this example, and we see most of them are really, really close in terms of time. All of them in the same month in the year, in the beginning of December, and in terms of the departure time, all of them are within half an hour of each other. However, when we look at, for example, at the airports, we see that they are all over the place. So somehow it picked on the time, the model trained just by looking at the time very precisely, but almost nothing but that. And as we kept going, we realized that we just forgot to add any features about the weather. Right? So it had to pick on something in order to infer the weather, and it found, okay, early December, this is the best approximate that I can have for the weather. So here's an example of how we use this kind of method to find missing features. So to summarize, what I was trying to present here today is a method that kind of is trying to be generic as a way to debug machine learning tools. Generic both in the way, in terms of the data types that it can handle and the type of algorithm that it can handle. And it's interesting to note that it goes beyond just debugging. It also allows you to rational around predictions that the model makes. So imagine you're building something that will be used by a physician in the clinic to predict whether their patients should be sent to home with chicken soup if they're sick, or should be sent to the ER. So you can build this black box that will make the prediction, but the physician would not trust it, because the physician would like to see why. And one way to give this why is by this hint. If I can show the physician, here's a list of similar patients and what were their outcomes. Now the physician can see whether it matches what the physician sees or not. Thank you very much.
All right. to